Science and automatic control. In this session of this year, we are working in a virtual form. And here you are very welcome to the communication systems session, where we have 4 research works, as you can see in the screen. Let's start then with Fernando Lopez-Marcos, who is reading with his presentation. Go ahead, Fernando.
Thank you, Doctor. I'm going to show my presentation. Can you see the presentation? Excuse me? Yes.
Yes.
Okay. Let's go.
I recall you that this session is being recorded.
Okay, thank you. Again, good afternoon, everybody. My name is Fernando Lopez, and I'm going to present this work titled A Fractal Octagonal-Shaped Transparent Antenna for C-band Applications. Well, the goals for this presentation are, first of all, make a review of the C-band. We talk about frequency range, applications, and relevance for this band. Also, we show the results of the analysis and design of a transparent antenna that operates in the C-band. And after all, finally, we show the results of the measurements for this antenna, its reflection coefficient, and the radiation pattern, in order to conclude with a comparison with other work presented in the literature. The C-band is one of the most important channels in electromagnetic spectrum. This band covers the frequency ranges between 3.4 and 4.2 gigahertz, and offers one of the best balance between bandwidth and no line of sight communications. This band was selected to be the main channel for 5G telephony systems. Although there are selected many frequencies in the UHF and KA bands, a C-band was selected for the main because of this relation between bandwidth and no line of sight. Due to massive usage of the C-band, its applications includes not only wireless communication, but also energy harvesting systems, as an example. The relevance for this band motivates us to design an antenna that operates in that frequency ranges. The design features of the antenna are shown next. This is the design of the antenna. First of all, we designed an octagon patch as a radiation element. The initial resonance frequency for this patch is calculated with this equation, and it's in function of the patch diameter, the relative effective length of the patch, and the separation between the patch and the ground plane. In this slide, we present a fractal modification that was made in the octagonal patch. We take two sides of the patch, denoted with this end letter, and focusing in one of them, the side is divided with a half of an octagon. The number of the sides of the next octagon is denoted with this letter S, with of the second octagon is equal to one side of the main octagon. This process of replication is made 3 times, and it's denoted with this letter N. The fractal dimension is calculated with this equation, and meanwhile, the electric effective length is calculated with this equation. The designed antenna is shown here. It consists, like we have explained, as an octagonal patch fed by a coplanar waveguide. A coplanar waveguide was selected because the resonance and the ground plane are both at the same plane. The selected materials for this antenna was as a substrate, a 1 millimeter glass, and as a conductive film, 150 nanometers indium tin oxide film. This material was gotten through the manufacturer Adafruit Technologies. The fabricated antenna is shown in this slide. SMA plug was soldered with indium spheres, and the union was reinforced with conductive paint, as we showed in this picture. Using the software Ansoft HFSS release 13, it was simulated the reflection coefficient for different iterations of the fractal structure. The results are shown in this slide. The electrical length have an increasing with a great number of iterations. The simulation of the reflection coefficient with no fractal structure is in continuous line, and the iterations of the fractal structure are denoted with a pointed line with 1, 2, and 3 different iterations. With the increasing of the number of iterations, the electrical length of the antenna decreases, electrical length of the antenna increases, and the resonance frequency for the antenna decreases. In this slide, we show the characterization of the reflection coefficient in function of different sheet resistance of conductive film. The manufacturer of the conductive film declared a sheet resistance of 10 ohms over square, but we also simulated with 12 and 14 ohms over square. The reflection coefficient for the antenna was measured using a VNA, a vector network analyzer. The results of the measurement in comparison with the simulation are shown in this plot. The reflection coefficient is 1.1, got a peak value of less 26 dBs at 3.95 gigahertz. The variations between the measurements and the simulation are due to the variations of the conductive film in the selected, and also of the variations in the fabrication, especially the separation between the feed line and the ground plane in the antenna. The radiation patterns of gain for the antenna was measured also in E and H plane. These plots shows a comparison between the simulation and the measurement of the radiation patterns. We got a peak value of less 6.9 dBi of the gain. There is a table that compares the results of this work with other results found in the literature. The obtained reflection coefficient and the gain for the antenna is in the range of other transparent antennas. Note that the low conductivity of the transparent film has a consequence of the low gain for this type of the antennas. The dimensions of the transparent antenna are between 30 and 90, shorter than the dimensions of other transparent antennas that are found in the literature. The conclusions for this work, first of all, the application of a Minkowski-like fractal structure decreases likely the resonance frequency and improves the reflection coefficient in the decider operation band. The bandwidth of the antenna is longer than expected and covers all the frequency ranges for the C-band. And the other conclusion is that the antenna gets a reduction in dimensions compared with other transparent antennas with a low change in the gain. The radiation patterns shows an unidirectional behavior with a gain that is in the range of other works presented. There are the references for this work, and this is it. Thanks for your attention.
Thank you very much, Fernando. Congratulations for this interesting work.
Thanks, Doctor.
Somebody have a question, please? No? Okay, I have some simple questions. If you can return to your radiation pattern, where you compare the simulation, and there is fine. Thank you. How do you take the measurements of the radiation pattern? Because yes, you explained very well about the reflection coefficient, but not about the radiation patterns, please.
About the radiation patterns. The radiation patterns was taken the measurements in a Faraday camera. we make an link budget between an antenna that gets that the gain of this antenna is known. So we transmit in the frequency as signal in the frequency peak 3.95 gigahertz, and after all, with a spectrum analyzer, we take the power that it's got with this antenna. Then, if we know the power that is transmitted, the gain of the transmitter antenna, and the distance between both antennas, we can measure with the Friese equation that characterizes the link budget. In this equation, the Friese equation, we can obtain the gain for this antenna.
Okay, okay. Thank you very much. And what about are you expecting to have omnidirectional pattern for application in 5G, don't you?
Yes, we expected an omnidirectional behavior due to the geometry that we take. The monopole antennas that are in the type of this work normally usually take an omnidirectional behavior. So this result was expected because of the geometry selected at the principle of the article.
Okay. It would be interesting if in a future research you can consider beamforming, because for 5G is now a very important technology to be implemented in the different devices, right?
Yes, that could be a great
All right.
hint. Thank you.
And finally, if you please go to the conclusion slide.
Here.
Yes, that's right. Okay, you say in the second budget that the bandwidth of the antenna is longer than expected and covers all the frequency range for the C-band. What happened about the interference if you are longer than the expected?
This could be a trouble, especially in the application of 5G technology, for example, because of the nature. But also the geometry selected for this band is expected a result like this. The monopole antennas even have not only a wideband but also an ultra wideband for applications. The bandwidth for this antenna is reduced because of the low conductivity of the film. If we take a copper antenna, for example, it's expected that the bandwidth increases because the monopole antennas with a radiation pattern with a geometry like this, it's expected that the bandwidth is bigger. At the beginning of this work, we selected this geometry because we are not sure that the frequency ranges could be covered with another geometry. In the literature, a lot of transparent antennas are presented with like monopoles. For example, with a circular patch or a ring patch or a hexagonal patch. There are.
Yes, that's right. Okay, right. Thank you very much.
Thank you.
Fernando. Okay, let's go ahead then with the presentation of Lizeth, please.
Hi, okay. I can't share the presentation. I don't know if I have the rights.
Ivan, can you help her, please?
I have here registered Marco Cardenas as the speaker.
Yes, I'm
Yes.
sorry. Yes, I said at the beginning that I was the person that I am going to present. I'm sorry.
Okay, so
For that.
let me change.
Yes, please.
Lizeth.
Okay, thank you.
You're welcome.
Okay, so good afternoon. So this is Lizeth Lopez-Lopez, and I'm going to talk about the advantages of exploiting the implementation of superimposed training in the context of spectrum sensing to improve the energy efficiency in cognitive radio. So this work has as a title on the leverage of superimposed training for energy efficient spectrum sensing in cognitive radio. First, I'm going to give you a brief introduction, and then I'm going to describe the spectrum sensing model that we are considering this work, and then I'm going to talk about the energy efficiency, considering a local spectrum sensing scenario, and then a cooperative spectrum sensing scenario. Then I'm going to show you the results and give you some conclusions of the work. It is a fact that the efficient utilization of the radioelectric spectrum is necessary to satisfy the requirements of future wireless communications networks. However, recent spectral occupation studies have shown that some portions of the spectrum are not being in use in determined time or geographical locations, which shows the inefficient utilization of these resource. Cognitive radio aims to improve this efficiency by allowing cognitive users, also known as secondary users, to access the frequency bands that are not being used by the primary user, which is the user that has a license to transmit in that frequency bands. To identify the available frequency bands, cognitive radio users cognitive radio users may draw on spectrum sensing. However, this task increases the energy consumption in the cognitive radio terminal. Indeed, since this task must be performed periodically, the increment in the energy consumption can be significant. Can be a challenge for the terminal, especially for battery constrained terminals. The average consumption on the terminal depends on the time used for spectrum sensing and the time for data transmissions, which also impacts the spectrum efficiency. For example, if we increase the spectrum sensing time, this improves the detection performance. However, the time left for data transmissions can be reduced or can be too short, so the secondary user's throughput can be might be affected, and also increases the spectrum sensing phase, increases the energy consumption used in this phase. On the other hand, if we reduce the spectrum sensing duration, we decrease the energy consumption of this stage. However, reducing the spectrum sensing phase reduces the detection performance. Also affects the secondary user's throughput, since more false alarms. Since we can have more false alarms or misdetections, which also generate interferences to primary users' transmissions. So improving the energy efficiency might implicate a reduction on the spectrum efficiency. Actually, these two metrics are related in the sense of they depend on the time used for spectrum sensing. So if we improve the spectrum, the detection performance, we can then improve the energy efficiency. It is known that if we take advantage of some known information about the primary user signal, the detection performance can be improved. In this case, the scar phase sensing method improves the detection performance by exploiting the superimposed training sequence in the primary user. Then we are considering a scenario in which the primary user implements superimposed training and the secondary user takes advantage of this technique of the known training sequence. So in addition to the advantages of that the uses of superimposed training implies in the primary user and the secondary user network, as shown in this figure, this technique might benefit also the energy efficiency. Superimposed training is a technique that has been introduced for channel estimation. So it is essentially implemented as shown in this figure, in where a training sequence is added to a data sequence and then transmitted. So for the spectrum sensing model, we consider a cognitive radius scenario with one primary user and one secondary user. When the primary user implements superimposed training and the secondary user performs spectrum sensing with a frame structure as shown in figure, where this is the total frame duration and represents the sensing duration, and this is the duration of the data transmission phase. Then, in order to improve the detection performance, we consider that the secondary users knows and take advantage of the superimposed training sequence by employing a simplified version of the scar phase sensing, which is shown in this figure. This method allows the secondary user to perform a training sequence synchronization to exploit this training sequence to improve the detection performance. So it consists of an energy detection part, a synchronization, and then a metric that takes advantage of the training sequence. And then these two metrics are added and then compared to a threshold to determine if the primary user is present, which is represented by hypothesis 1, or if the primary user is absent, which is represented by hypothesis 0. The detection performance of this method is the following. Considering that we are considering that each sample of the received signal at the secondary user has the following distribution, where sigma squared represents the noise of the noise variance, sorry, and sigma d squared represents the power of the primary user's data signal. And then we have we consider that this is the amplitude and phase of a wireless channel gain, and this tau represents an unknown shift in time, which represents the lack of training sequence synchronization. And this the scar phase sensing allows the secondary user to estimate this tau. Then the probability of false alarm is given by this equation, which depends on the number of sense samples or the number of samples used in spectrum sensing, and a value here which is the training to information ratio. And this parameter is specified by the primary user. Then the probability of detection is given by equation 3. And with these values. And about the energy efficiency, in the context of cognitive radio, the energy efficiency is defined or can be defined as the number of bits transmitted by the secondary user per unit of energy consumption. So this is the relation between the secondary user's throughput and the average energy consumption in the cognitive radio terminal. To determine the secondary user's throughput and the energy consumption, we have to consider some scenarios. These scenarios are represented in this figure, in which we have the activity of the primary user. For example, it can be absent or present, and the activity of the secondary user. For example, the secondary user can decide the presence or absence of the primary user signal and transmit data. For example, the case 1 is when the primary user is absent and the secondary user decides the absence of the primary user, then it transmits data. And the case 2 is when the primary user is present and the secondary user decides the absence of the primary users and transmits data. The case 3 is when the primary user is absent and the secondary user decides the presence of the primary user and waits until the next sensing phase. And finally, the case 4 is when the primary user is present and the secondary user decides the presence of the primary users and waits until the next sensing phase. So we have to determine the probabilities of one of these, of each of these cases, which are as follows. So for the case 1, we have the probability given by this, where this is the prior probability of the primary user of being absent, and then since the secondary user is allowed or transmit data, the secondary user is given by equation 5. Where this is the SNR of the secondary user's link. And in this case, the energy consumption can be calculated as shown in equation 6, where PS is the power for sensing, PC is the circuit power, and PT is the power or the transmission power. And in the case 2, this is when the secondary user incorrectly decides the primary user's presence. The secondary users does not transmit data. Then the energy consumption is given by this, and this is only the power used for sensing and the circuit power. And in case 3, the secondary user incorrectly decides the absence of the primary user with this probability, where this is the prior probability of the primary user being present, and the secondary user transmit data, thus the throughput is given by this equation. And finally, in case 4, the secondary user is not allowed to transmit data, and the energy consumption is given by equation 7. Finally, we have that the average secondary user throughput is given by equation 9, and the energy consumption is given by equation 10. For the comparative scenario, we consider one primary user and k comparative secondary users with a fusion center that implements an OR rule to decide if whether the primary user is present or absent. In this case, the overall probability of false alarm is given by equation 11, which also depends on the number of cooperative secondary users, and the overall probability of detection is given by equation 12, also depending on the number of secondary users. In this case, and we consider a frame structure as shown in figure 7, where it is also considered the time for reporting the message to the fusion center. Analyzing the 4 cases, the average throughput of the cognitive radio network is given by equation 13, and the energy consumption is given by equation 14, which also depends on the number of cooperative secondary users. Then we have some computer simulation results. These are some of the parameters used in the simulations, and I'm going to just specify some of them. For example, that we consider a probability of detection of 0.9. We consider that the training sequence is assigned as here, and the period of the training sequence is equal to 10, and we have a tier value of 0.2. And we consider a scenario where the an SNR in the secondary users link is 5 decibels, and in the primary user link is minus 12 decibels. So first, we have the achievable secondary users throughput as a function of the sensing samples for the simplified scar phase sensing, and we compare it when the secondary user does not take advantage of the training information. So we compare the results with the energy detection. And here we can see that the throughput is better, or the secondary users achieves a better throughput when exploiting the training information. And the maximum throughput is attained with less number of samples in comparison with the energy detection. Then we have the average energy consumption. In this figure, it can be seen that the average energy consumption increases when using the simplified scar phase sensing. However, we have a better throughput, so even we have more energy consumption, we can have an improved energy efficiency. For example, as we can see in this graphic, or in this plot, where it is shown the energy efficiency as a function of the number of sensing samples. And we can see that the simplified scar phase sensing attains a better energy efficiency than the energy detection, and with less number of sensing samples. So this means that to satisfy a determined detection performance, we can reduce the time for spectrum sensing without compromising the detection performance or the secondary user's throughput, and improve the energy efficiency. And this is shown in this figure, where the number of sensing samples to achieve a maximum energy efficiency and a maximum secondary user's throughput are shown as a function of the SNR. For example, we can see in minus 14 decibels that for the energy detection, the number of samples to achieve the maximal throughput is around 4,100, and the number of samples required to achieve the maximum throughput is around 2,500, and this means that if I choose this number of samples that this number of samples that maximizes the energy efficiency, then my secondary user's throughput is decreased And in the contrast, for the simplified scarf phase sensing, we have that the values are closed, the required number of samples are closed, so we can maximize the energy efficiency without compromising the secondary users' throughput.
Lizeth, can you conclude, please?
Yes. And well, and this is shown here, no? We have the maximum throughput and the obtained throughput. So the difference here is less than the difference in the energy consumption. Then we have the results for the cooperative scenario where it depends on the cooperative secondary users. As a conclusions, we have that we analyze the energy efficiency and the relationship with the spectrum efficiency when using the scarf phase sensing. And we show that when using the scarf phase, we can improve this energy efficiency with less reduction on the spectrum efficiency. And more studies about the trade-off between the spectrum and the energy efficiency are needed under a superimposed training scenario. Thank you.
Thank you very much, Lizeth. Thank you a lot. Very interesting indeed. Anybody have a question?
Okay, I can't.
I have a question, Lizeth.
Okay.
Please. Yes, Timoteo, can you wait, please? Thank you very much. Okay. The idea is to give a priority to the energy or to the bandwidth, don't you?
Yeah.
In some sense, right? You are comparing energy and bandwidth. This is the problem that we have in communication, right? Okay. And then in your model, you are talking about one primary user and one secondary user. Is correct?
Yes.
All right. Okay. What do you expect with different distribution of users? I mean, in this case, you have the same number of users. In this case, just one primary and one secondary user. But what do you expect if you if you change this distribution?
Okay. If you, for example, when more secondary users are considered, we have more energy consumption, but we have a better secondary users throughput. So, for example, we can have an increase in the consumption during the spectrum sensing. However, the energy efficiency might be also improved with more number of secondary users since the detection performance is improved. Actually, we have to make more analysis because also it depends on the rule used in the fusion center. It also depends on the channel experience in each secondary user. So I would say that primarily that essentially it depends. Although the energy consumption is increased, the spectrum efficiency is improved or can be improved.
Okay, thanks a lot. Anybody else have a question? No? Okay, thank you very much. Congratulations, Lizeth.
Thank you.
All right, okay. Now, Timoteo, it's your turn.
Okay, thank you. Can you hear me?
Yes.
Can you see the presentation?
No yet. Yes, it's coming. It's ready. Okay, go ahead,
Okay,
please.
thank you. I am going to talk. Good afternoon, everyone. I'm going to talk about self-localization of sensor nodes and of a wireless sensor networks. And the contents of this presentation is this. This is divided into 5 points. And the first point, I'm going to talk about introduction. And the second one, which is the core part of this presentation, I am going to talk about the algorithm that we are proposing. And next, in the third point, I am going to show you the results obtained from simulations. And finally, in the last point is the conclusions of our work. As we are talking about wireless sensor networks, I think it is necessary to clarify what a wireless sensor network is. And in this slide, you can read that it is a collection of sensor nodes, and that the main characteristic of these sensors is that they are small and low cost, and they are limited in power also and low computing capabilities. So this is the core characteristic of sensor networks, and the algorithm that run inside a node, a sensor node, should consider this characteristic. The main applications of this wireless sensor networks are shown in this slide, and we mentioned here some of them: the forest, the plane, home, factories, and transport. And a good example of these applications is the military one, when the sensors are deployed in the battlefield, and these sensors need to know, based on observations, if a movement belongs to a friend or an adversary. This is kind of a good example of application of sensor networks. And in all of this application, the localization of a node is really important. And as sensors are deployed randomly, localization plays a key role, because the measurements doesn't have any sense if there are no knowledge about the localization of the sensor. In this slide, an example is put. Imagine that you need to sensor a temperature in a field, and the sensor needs to send both the temperature and the coordinates where this temperature was measured. So because of that, there are a lot of related work on localization, but in this work, the nodes are considered as static, but it is not the case always. Sometimes the nodes are mobiles. It is necessary the movement of some of nodes in some applications. And this is necessary because the mobility has some advantages. And in this slide, I have mentioned 3 of them, 3 advantages. And I enumerate 3. The network connectivity is improved, is one of them. The second is the energy consumption is balanced. And finally, the coverage, it is increased. And about the localization of sensor nodes in the mobility case, one must consider the latency, because it is necessary to take into account the latency on localization. It becomes more crucial than in the static counterpart. So I'm sorry. So in this part, we can set the problem of localization in a wireless sensor node application. And I have wanted to mention here that there are 2 types of nodes. And the first one is called the anchor or seed nodes, and these nodes have their position all the time. But the other nodes, which is most of them in a wireless sensor network, they are called the blind nodes, and these nodes need to know its position based on the measurements obtained from the position sent by the anchor nodes. And in this problem, we are considering that all nodes are moving, and that the sensor, that the blind node can measure its velocity. So in this slide, you can read how can the problem of localization be stated, and it is necessary here to mention that the model that we are using to measure the velocity of the sensor node, it is considered as a zero mean Gaussian random variable. Okay. In this proposing, we are we are based our proposal on the Monte Carlo algorithm, and the localization problem can be stated can be stated as a non-linear filter problem, as in this equation can be observed. In this case, xk is the position of a sensor node at instant k, and OK is the observation received by a sensor node at instant k. And the Monte Carlo algorithm, or the can be the nonlinear filter can be seen as a Bayesian point of view, and the Bayesian point of view considers that it is necessary first to construct the probability, the posterior probability density function, in order to obtain the variable xk. So the problem is to how to construct a PDF, posterior probability density function, and from that obtain the state xk. Usually, what is done is that when we have the PDF, the xk is estimated as an average of this PDF. So this is the Bayesian point of view, and this is what Monte Carlo algorithm follows. And the Monte Carlo approach, or the idea behind the Monte Carlo approach, is that this PDF can be represented as a weighted set of samples, and this set of samples, all of them, or each of them, has a weight. This weight is usually from 0 to 1. This weight is normalized. So if we can obtain a set of samples that represent a PDF, we can also obtain an xk state only by averaging that PDF. That's the idea from the Monte Carlo approach, and that's the idea that we are following here in this work. And the observational models that we are using in this work is that the first observational model is the one that I have mentioned previously, which is the velocity measured by a sensor node, and it is considered as a zero Gaussian noise. And the second observational model is the also well-known shadowing model, and this it is expressed in terms of decibels, and it is expressed as a Gaussian PDF. Of course, the observations that receive a sensor node are, I repeat, are sent by the anchor nodes. That is important to say again. And basically, what we are doing here is that we divide the Monte Carlo method into two steps. The first step is the prediction one, and the second step is the update, in order to obtain the PDF that we require. And in the prediction step, as we can see here on this slide, we can consider an example. We can consider an example here. The figure shows an example of a sensor node, which is represented by the point, and a group of seed nodes, which are represented by a upper triangle. So when this sensor node receives the three measurements, the three coordinates from this seed or anchor nodes, it can form a prediction region. In this case, we can form a rectangular prediction region. So the prediction consists of propose a sample or a group of samples, a group of coordinates inside this prediction region. This is all what a prediction region is about. And the next step, which is the updated step, consists of assign a weight to each of these samples. And the Monte Carlo algorithm proposed that these samples can be assigned by the observational PDF. In this case, is the PDF that is expressed in decibels, the PDF of power loss that I have shown previously, and the first expression that you can see in this slide tell us or give us the weight of each sample. As you can see, it is depend of the number of seeds that a sensor node can hear in an instant K. As the normalization, as the weights needs to be normalized, the second expression gives us the normalization of weights. The weights should be from 0 to 1, and the second expression in this slide, it is for normalize that weights. But sometimes when we are collecting the samples, some samples or most of them have a 0 weight. This is a problem because in this moment the PDF obtained cannot be represent the PDF real. And what we need to do in this case is to resample, is to follow a resampling process. This resampling is obtained from the sampling set obtained previously. And to decide if this resampling is necessary, one need to check this with the expression shown in this slide, the first expression. And if it is necessary, the resampling is done. And finally, the node position is obtained by, as I said, averaging the set of samples, and that's it. And that is as simple the Monte Carlo algorithm. And this is what we have done in this paper, and this is what we are showing here. And to prove our proposal, I have done some simulations, and the scenario considered in this simulation is shown in this slide. The number of seeds or the number of anchors range from 4 to 25. The coverage radio is supposed to be 30. And the nodes are moving in a square region from these measures, and the number of samples considered to form the PDF are 50. And for the shadowing model, we have proposed these values. The variance from 4 to 8, and the exponential from 2.3. And the results obtained are shown in this slide. First, we have done a transient analysis, and in this case, we are comparing two ways. And the first case is when the seeds are static, and in the second case is when the seeds are mobile. As you can see, when the seeds are static, the error is the performance is better than when the seeds are mobile, and the steady state is reached when is reached first when the seeds are static than when they are mobile. The second simulation that we have done is by varying the maximum velocity of a sensor node, and as the intuition tells us, this it can be seen that the better the lower the velocity, the maximum velocity, the better the performance of the algorithm. And we are comparing this algorithm with the multilateration algorithm, and we can see that the results are better for the algorithm that we are proposing than for the multilateration algorithm. The third simulation that we have done, we're varying the shadowing. We are varying the shadowing from 3 to 8, and we are obtaining here also a better performance of the algorithm that we are proposing than the multilateration one. So in this case, it is also remarkable that that when the seeds are static, the algorithm's performance is better than when the seeds are mobile. And finally, we have varied the number of seeds, and as the intuition tells us, again, if we increase the number of seeds, it is better in the performance of our algorithm. And of course, the multilateration algorithm are worse than ours. And the conclusion of this work are shown in this slide. One of the main contributions of this work is that we are take out the previous works that we encountered in the literature about Monte Carlo methods, and we are propose a more realistic models to study the performance of Monte Carlo method. And we are considered also a sensor that is more powerful. I mean, a sensor that can measure the velocity, and we think that it fits better with the current state of technology. And other conclusions that we are taken is that the simulation shows that our proposal is better if we compare it with multilateration, with the multilateration algorithm, and that when the nodes are static, the algorithm is better than when they are moving. And this is remarkable because we are not taken into account if the seed nodes are mobile or if they are static. And one of the factors that affects the performance is the shadowing. And I think this work could be a good starting point to propose new models, to propose new algorithms that cope with this problem. And we are considered here in this work the uncorrelated shadowing. And in next works, we are thinking to work with a correlated shadowing model. We think that we can improve the performance of the algorithm if we consider this phenomenon. And this is all about this presentation. Thank you.
Thank you very much, Timoteo.
Thank you.
Anybody have a question? No? I have some simple question. Very interesting indeed. This work about the localization is a very problem actually. All right. Okay. You mentioned at the very early of your work about the latency and Doppler effect. And in fact, you are considering the movement of the...
I'm sorry, I didn't hear you.
Can you hear me?
I have some problems with the sound.
Right. Me there? Can you hear me there?
I'm sorry, no, I can't. Yeah, here, I can hear you right now.
Okay,
yes,
can you hear me? Yes, all right.
But
okay.
I can't hear your question. Yes.
Do you hear me now?
Yes.
All right, okay. I talk about in the very early of your work, you mentioned about the latency and Doppler effect, right? And you say that it's very important for this type of work, but I don't see anything about in your simulation or something that you consider the Doppler effect, for example. Even the nodes are in moving. Do you expect in a future work to consider the Doppler effect if it has some relation with the probably localization?
Yes, of course. The Doppler effect and the latency are two of the more important phenomena that it is necessary to take into account in the localization. In this case, we have not considered this because we needed to study the Monte Carlo algorithm and in a more realistic way, and not in the like in previous works, not in the idealized free space scenario. So we didn't simulate the latency and the Doppler effect, but in the future, I think that it is necessary to consider both of them. And the latency is, as you probably know, is the time required to run the algorithm in short way, said in short way. And in this case, as the algorithm is so simple, I think the latency will be it is not a problem, and that's it.
All right. Okay. Excellent. Now, when you introduce the shadowing effect, do you have any reason to use that specific value for the shadowing? I mean, in the terms of the standard deviation, etc.
Yes, we have used the values that are reported in literature that are considered to model a more an urban case, and we needed to simulate our work in this kind of environment. So we took, or I took this value to do my simulations because they are reported in the literature. That's it.
All right. Okay, but that means for a specific scenario.
Yes.
You see? All right. Yeah. Okay. Are you talking about of urban, rural, suburban scenarios or something like that?
In this case, no. We are only consider the scenario, the urban scenario, and we are not considering the other scenarios.
All right.
I think in the future we can consider most of them.
Okay. Okay. Excellent. Thank you. Okay. If anybody have another question? No? All right. Thank you, Timoteo. Congratulations.
Thank you. Thank you very much.
Now is my turn. It's the last work. Let me share the presentation. Yes, let's see. All right, here. You can see the presentation. Ivan, yes. You can see the presentation? Okay. Okay, let's start. Yes. This last work in this communication system technical session of the CCA 2020 is entitled Preliminary Study of Space Weather Effects on the HF and VHF Communication at low latitudes during an early stage of the solar cycle. We are 5 authors of different institutions, as you can see. First of all, we have the Aerospace Development Center of National Polytechnic Institute. Here from CIMBESTAB, Center for Research and Advanced Studies of National Polytechnic Institute, the University of Colima, the Complutense University of Madrid, and the Mexican Federation of Radio Experimenters. The contents of the presentation is organized in this form. First of all, I will present an introduction, then the space weather conditions, some experimental settings, observation and data analysis, and a final discussion, and finally the conclusions. Then, probably many of you know about the transmission using the ionosphere layers, and it's very common. In fact, it's the first approach to achieve communication in a very long distance. In the early of the century 20, it was demonstrated the existence of these ionospheric layers, and it was the form that the Marconi achieved the transmission from one continent to another one. So we have HF, high frequency signals, and they reflect in the ionosphere, and we have also some lower, very high are reflected in another ionosphere layers. Basically, that's the idea. On the other hand, we have probably many of you have heard about the solar cycle, and it is mentioned from the American Space Agency, NASA, that every 11 years or so, the sun's magnetic field completely flips. That means that the sun's north and south poles switches places. Then it takes about another 11 years for the sun's north and south poles to flip back again. The solar cycle affects activity on the surface of the sun, such as on sunspots, which are caused by the sun's magnetic field. As the magnetic field changes, so does the amount of activity on the sun's surface. Okay? Now, today, we are in the solar cycle 25. The temporal variability of the ionosphere is related to what is called space weather, provided that it describes different parameters of the sun activity and their effects on the Earth atmosphere. Moreover, the space weather parameters that impacts on the ionosphere behavior are different for different latitudes. In other words, there are different ionospheric compositions depending on the latitudes, and thus we can talk about a space-time ionospheric variation. So, in this paper, a set of observation of performance of radio ham system operating in Mexico at low magnetic latitude at the HF and VHF frequency band is reported and analyzed. The observation period was during the spring 2020 and therefore corresponds to an early stage of the solar cycle 25. What about the space weather condition? The most relevant characteristics of the space weather during our study period is about 17 days between May and June, are the very low level of solar activity and the almost total absence of sunspots on the sun photosphere. Continuing with the trend of the last year, when the sun was blank 70% of the time, the current year presents a similar percentage of blank days so far.
Sorry,
Yes?
but we can't just see the first slide.
The first what?
The first slide. In your presentation?
Yes?
It's just the first page.
The first page? That one?
Yes, the first what we can see just.
All right.
So maybe you can refresh, or
Okay.
in some other presentation, we can solve this if you turn off your camera when you present. So
All
maybe
right.
the net.
Okay. Let me stop the camera. Can you see the presentation there?
Yes, that is just the first.
The second one now?
No.
Okay, let me see. Let me see.
Okay, now the second one.
Let me stop the to share the presentation. Okay, let me see. Let's see. You see my presentation there?
Not yet. Yes. Now we
Right?
can see. Right.
Yes.
Yes, this is the first one.
Now the second one,
Second one, yes.
right? Now let me see if you see that one and then one. You see the second one?
Yes, second one.
All right. Let's see. Start then. Okay. Let me continue here. You see this number 4?
No, just the second one.
The second one is frozen in the second one.
Yes.
Okay. Okay. Now you see the first slide.
The third one. Now the third one.
The fourth one, you see?
Fourth one. Yes.
All right. Okay. I use in this manual form, right?
Yes.
Okay. Thank you, Van. Okay. As I let me briefly outline about this slide to not take a lot of time. It's about the transmission around the ionospheric layers, and I say about the high frequency signals and very high frequency signals in this reflection in different layers of the ionosphere. Then I define the solar cycle as the American Space Agency NASA defined, and as you have probably heard about the variation every 11 years or so, we have some peculiar behaviors of the sun activity. On the other hand, the temporal variability of the ionosphere is related to what is called space weather, provided it describes different parameters of the sun activity and their effects on the Earth atmosphere. Moreover, the space weather parameters that impact on the ionosphere behavior are different for different latitudes. In other words, it depends on the latitudes. And that we can talk about a space-time ionospheric variation. In this paper, we present a set of observation of the performance of radio ham system operated in Mexico at these different frequency bands. And they are reported and analyzed. The observation period was during the spring 2020 and therefore correspond to an early stage of the solar cycle 25. This better weather condition, the most relevant characteristic of this concept during our study period are the very low level of solar activity and the almost total absence of sunspots of the sun photosphere. The trend of the last year, when the sun was blank 70% of the time, the current year presents a similar percentage of the black days so far. So we observe that for example, the solar wind speed during those days, and we see a similar behavior in this parameter, but suddenly at the end of May, we can see how the solar wind is increased in this period. About the planetary index, it was very, very calm because it takes values from 1, 2, or even 0, and only to the end of May, it increased but very little. On the other hand, we take some measurements of the component age of the magnetogram generated from the data registered at the Teoloyucan Magnetic Observatory of the National University of Mexico. Let me see, then, okay. It was about the space weather condition during the experimental. Then, what was the idea of the experimental settings? A call of participation was open to members of the Mexican Federation of Radio Experimenters to have representative stations from the 3 zones in which radio amateurs are organized in Mexico. Here in this table, you can see the different identification or call sign of these stations and in which state of Mexico they are located. And this is the distribution of this station. As you can see, there were participant stations from different zones of the country, whose locations provide reference points to evaluate the propagation effects existing within Mexico. Most of participants of the campaign carry out their observation preferably in the morning to avoid an electric or rain thunderstorm that could affect the quality of communication links. Then the observations are described in what I'm going to explain you. We divide the observation into groups. On the one hand, in the 40 meters band, that means in 7 megahertz frequency band. Then for low Earth orbit satellite at 145 megahertz for downlink and 435 megahertz for the uplink. In this picture, you can see the footprint of one of the amateur satellite that for 1 day of the observation period. Then for this station, here a plot of the received power during these observation days. And we see that the behavior was very, very stable. But again, for the end of the May, we start to see a reduction of the received power of some terrestrial station. About the satellite stations, we didn't appreciate remarkable variation as in the ground station, as we can see in the other band. So, as a final discussion, it is worth including a short comment about the absence in the period of observation of phenomena as a heavy rain or hurricanes that can affect the ionosphere and its influence on the transmission of electromagnetic waves. Because no strong earthquakes or significant meteorological phenomena didn't occur during the period of observations, the possible influence of space weather in these frequency bands was studied without perturbation. We are sure about. The results only indicate a small reduction on the power and the received power levels when a small variation of the geomagnetic fields are present. And as a conclusion, during this period of low solar activity, the propagation condition at HH frequency, particularly at 7 megahertz, didn't represent significant problems in mail communication among radio amateurs within Mexico. Nevertheless, we found a generalized reduction on the received power levels of the last day of the study period. This situation coincides with a small variation of the magnetic condition due to the solar activity. On the other hand, results analyzed for LEO satellite links operating at VHF in the downlink showed a very stable behavior both of the phone prints and the received power level, which indicates that the relatively calm solar activity didn't impair these radio links. Results analyzed and shown in this paper are the basis for future studies about the relationship of possible effects of the solar activity on radio communication, particularly at radio ham frequency bands, taking as a baseline the evolution stage for the current solar cycle. Basically, this is our idea. Thank you very much for your attention. Any question? No question?
I have a question.
Yes, thank you, Marco. Tell me.
I think this is a very interesting work. I am reviewing the paper here at this moment, and I can see this is something that is related to the radio experimenters or ham radio enthusiasts in Mexico, and I didn't listen, but for example in figure 5 in the paper where when it is shown all the stations that participated in the study in Mexico, so this means that many other stations could have taken part of this study, as I understand, right?
Yes, that's right.
And if more stations will have participated, how does that have changed the results that you get?
Yes, I think that probably it doesn't change in a significant form, because unfortunately for those days, the sun activity was very, very calm. But for the moment, it were the station that they participate. But yes, it's very interesting to invite, or that the colleagues accept to participate in that type of experiment. Yes.
Yeah, well, thank you very much. I like this work a lot. It has very interesting ideas and results here that you are presenting. Thank you.
Thank you, Marco. Anybody else have a question? No? All right. In this form, thank you very much for all the authors participating in this technical session.
Question?
Yes?
Okay, so let me read the question.
All right, okay, go ahead.
Because I cannot see the messages. Okay, it's here. Okay, the question is by Angel Adrian.
Okay.
What can we do against solar electromagnetic activity? It seems as an impossible humankind work.
Sorry, can you repeat the question, because it's very difficult to hear you, please?
Yes. What can we do against solar electromagnetic activity? It seems as an impossible humankind work.
I honestly, I don't understand very well the question. The human activity, how the human activity affect the electromagnetic waves?
What can we do against solar electromagnetic activity?
Okay. Unfortunately, we can do anything about, because the sun is very independent of us. But anyway, maybe, for example, for the GPS is some strategies are taken for the localization systems, in fact, to prevent some effects that interrupt the normal operation of the different electronic equipment during this during some more activity of the sun. I don't know if it's answered the question.
Well, we don't have another answer for the...
Yes,
Yes.
Angela. Okay, thank you, Angel. Anybody else? Nobody? No, Ivan? All right, thank you. Okay, in that way, we conclude this technical session for all the participants. I would like to thanks to the author for the interest to participate in this technical session, and for the rest of the participants. And we hope you enjoyed another technical sessions in this conference. Thank you very much for everybody. Congratulations to everybody, and take care, all of you.
Thank you.
Okay. Thank you, Ivan.
Thank you. Bye.
Welcome. Thank you.
Thank you.